in teaching, and if this is successful, then this will take us show a new way altogether in where distance teaching can go, because this is guided distance teaching as opposed to the model which the West has been proposing, and let's hope how this goes. Now, I will, my name is Sanjeev Sanghi. I am professor in the Applied Mechanics department at IIT Delhi. Before I start, I'll give my email where if you want to send queries to me, all feedbacks, I'm giving my Gmail address, which is my personal mail. So if you have any queries, any feedback, anything, please feel free to communicate with me. Maybe you can put in the subject you put QEEE statics, so that I know this is a mail from QEEE, and I will take immediate care to respond to you as soon as possible. So this is the way you can communicate with me. Now, I will be teaching to you some topics in statics, and from what I believe, the class which will be attending these lectures is a class of civil engineering students, and that is why since we had a small module of only 15 hours of lecture, not a full course, because we are just starting to do this, I decided to start from the basic topics which one has in engineering mechanics, that is statics. Now, what do we study in engineering mechanics? Mechanics basically is a study of motion of, it could be anything. It could be a particle, it could be a rigid body, it could be a solid body, it could be fluid, it could be anything for which we have the study. If something is moving, then what causes the motion? If certain forces are being applied on a body, how does it move? That is what we study in mechanics. Now, coming to the subtopic which we will be focusing on, we will be talking of statics. And what I just now talked of motion, statics is actually the opposite of that. Statics means body at a state of rest. So if in statics we deal with a body at the state of rest, then how does statics come under mechanics? Well, it is an integral part of mechanics, or maybe you can say the first step in mechanics, because in statics what we will study is what combination of forces are acting on a body such that the body does not move. And often that is what our aim is. If we are designing a structure which is supposed to be static, like a building which is not supposed to move, so then we have to design it in such a way that under action of typical forces which act on it, it does not move. Or even if it moves, then it moves in a way such that its motion is predictable. For example, when you design a building and there is a earthquake, we would like it to move not more than a particular limit. But all these will be part of further mechanics courses in our topics. So what I will like to now do is briefly, since this is the first class, list the courses which the topics which we will cover in this course. So I'll just start with that, but before that, let me talk about the textbook which we'll be using, and let me just show this to you. The textbook will be, I'll just write its name. It's Vector Mechanics for Engineers. It's a very classical textbook. So that is why I've decided to use this. Vector Mechanics for Engineers. Actually, this book comes in 2 volumes, or there is a combined volume. Now for this course, we will only be using statics, but if you also have to do dynamics, then the second part is dynamics and you could go for the combined version. And this is a classical text. The original authors were Beer and Johnston. Over a period of time, more people have added to the book. We had the third author, Mazurek, Cornwell, and finally in the last 2 editions, I have also contributed to this book. So these are the authors, and we will be following the 10th edition of the book as far as problems are concerned. Even the earlier editions, if you look at it, the theory is almost the same, so you need not be bound by the 10th edition. And as in India, we only follow the SI units, so we will be following only SI units in this course. We will not be following the British units. So this is the book, and this book is published by McGraw-Hill. So these are the some details of the textbook which we'll follow. Now what problems will be given, I will start doing that, and they will be put up on the website for the course a bit later. The homework problems you are expected to do. Let me briefly and quickly look at the topics which I expect to cover with you when I am taking this course, and this may also help in teachers who are there and who have to decide their full course. At least the topics which I will cover, I will write right now. I've already put it up. It must be there on the site for the course, but I'll just repeat it. So this could help you in deciding which student will come for this course and how to plan the other lectures of the course which I will not be taking. So I will start with an introduction to vectors. This will be a brief introduction. Some of this stuff you would have already seen, but I decided to include this topic because I was told that in the first week, some of the colleges may not come in. So as more and more colleges come in the first week, that is today and on Thursday, I will just deal basically with vectors. After vectors, I will go on to the next topic, which will be introduction to forces and moments. And here we will see what does a force do, what is the definition of a moment. Moment, as you will see, is something which is moment of a force. So a force is associated with a moment, or every force by itself creates a moment, and that is what we will discuss. What is the definition of a moment? And from here we will come to something new which you may not have seen. You have seen moment about a point, but we will talk of moment about an axis, and we will also see couples, which is a system of two parallel anti-parallel forces of equal magnitude acting on a body which cause a rotational effect. Then from forces, we will move on to the next topic, which will be equilibrium, and which is the crux of statics. So we will, when we talk of forces and moments, so here in equilibrium, we will be concentrating on equilibrium of a rigid body. So we will look at the topic of equilibrium in details. We will see what are the equations of equilibrium and how these equations can be used to solve problems of on the body, of equilibrium on a body. And when we talk of equilibrium, among the topics which will automatically follow will be the concept of a free body diagram, which is very important. And there we will see how different type of supports exert different type of forces or moments, or both of them, on a particular body. So equilibrium of a rigid body will be the next topic, where we'll look at equations and problems of how to solve the equations. And all the other topics which will follow, which we will do, will essentially apply the same equations of equilibrium. Then after we do the equilibrium, we will talk of centroids and center of gravity. Now what you'll find here is that actually before I do equilibrium, I will be maybe I should then flag that topic also. We will be looking at what are termed as equivalent force systems. And centroids and center of gravity are examples of equivalent force systems which I will be teaching, and I'll bring out the difference between these two, but the extension of equivalent force systems just happens to be centroid. And then we'll come to the next interesting topics which are related to real physical problems, physical real life problems which you as civil engineers will address, and this will be analysis of structures. And once again, the analysis will be pertained, or we'll restrain our analysis to only statics problem, that is structures which are not moving. When they move, then we come to dynamics, but we will focus only on structures, and here two particular things we will study. One is what we call as truss, which as civil engineers will be very important to you, and the second part will be machines, where we look only at the statics arrangement of the machines. This may be of importance but not as much important as truss are. And then we will come across, I think I'll have only time for that, and that is we will look at the concept of sectional forces in members. And what do we study here? If I cut a member, if we make an imaginary cut through the member, what is a member? Any mechanism, any body which 3 or 4 things connected together. If I make a cut, then in the cut, what forces and moments are exposed at the cut? And when we talk of sectional forces, we will introduce terms like axial force, shear force, and bending moments. Now, what we learn from here, the shear force and bending moment, they will be used in later courses, particularly your solid mechanics course, to design the members or beams, as you may call them. And finally, if I will have time, then I will do a bit of friction and how do we analyze problems where friction is involved. So without any further delay, let's start. The way I'm going to run these classes, we will, I think at about 10 minutes before the end, I will leave time for questions. But I think since we have a lot of colleges connected, these giving time for questions, I'm not sure, I'll try it out today. Let's see how fruitful it is. But otherwise, that is why I have given you my email address at the first slide. And I'll write it again at the end, my email address. So the best thing would be that if you have any doubts, please feel free to send email to me. I think that will be the more preferred way or the more useful way for you people. Because if I'm going to leave 10 minutes for questions, I don't think we'll be able to answer all the questions in 10 minutes. So therefore, feel free to send all your queries to me on the email address which I have there, and I'll be able to answer your questions. Okay. So now we start, as I told you, with the first topic, which is vectors. Now, this is a topic which you will normally study in mathematics. In your course in maths, in your class 11th or 12th maths, you would have studied vectors. How do we define a vector? And I think most of you have an answer to this, that vector is a quantity which has two parts, which has a magnitude, that is how big it is, and not only it has a magnitude, but it is also a directed quantity. So therefore, it has a direction. So a vector is which has two components to it. It is how big is the vector in size, that is what we term as the magnitude, and the other thing is a direction. Now we represent. Now this is just a notional definition of a vector. Actually, a mathematical definition I will come to in a short while from now. Now, if we represent a vector by, if we are using a textbook, then there will be a bold faced letter, or we put a letter with arrow on top. So for example, I want to show a vector P. I will show it with P along with an arrow on top. For me to write a boldface is difficult, but if you follow a textbook, you will see bold-faced letters being used in textbooks. Now, let us say I have this quantity P, which is like this. So we say this is a vector P. Another directed quantity Q. Now here the length of the arrow is supposed to be proportional to the magnitude. When we draw a vector, the length of the arrow is proportional to the magnitude of the vector. So if I draw two vectors, if one of the, for example here, P, I made it bigger, P has a length which is bigger than Q, and they represent two vectors of the similar nature of quantity in the same units, then the magnitude of P will be bigger than the magnitude of Q. Now, how do we actually define a vector? And for that, let's talk of addition of quantities. Suppose I have a scalar, or I have two scalar quantities. I have a scalar quantity, let's say mass of something which is 2 kg, another thing which is 3 kgs. So two scalars, one of magnitude 2, one scalar 2, another 3. If we add them up, the answer will be 5. 2 plus 3 is equal to 5. So this is how we add scalars. We can also subtract scalars. For example, if I have 2 minus 3, this will be minus 1, or I can also say I have added minus 3 to 2 and this is minus 1. So this is what I can refer to as algebraic addition. Now, in context of vectors, does this rule follow? And you'll realize it will not. For example, I have a vector P whose magnitude is 5 and a vector Q whose magnitude is 2. Then P plus Q may or may not be 7. P plus Q, in fact, you will realize it will vary from 3 to 7. But once I say, actually when I'm saying uh, P plus Q, it varies from 3 to 7. What I'm talking of is the magnitude of P plus Q. So the magnitude of a vectors will not follow what I mean is, if two vectors are added, it doesn't mean that sum of their magnitudes is equal to the magnitude of the two individual vectors. So then the question comes, how do we add up vectors? And this is actually what also gives us the definition of a vector. So now let us give a slightly more mathematical definition of a vector. And this definition says that a vector is a quantity with magnitude and direction which adds up according to the parallelogram law. In fact, as we will see, it is not just a parallelogram law. Sometimes we can also say it adds up according to the law of triangles. I will explain these two things, that we have defined a quantity, it adds up according to the parallelogram law. Now, what is the parallelogram law? Suppose I have a vector P which looks like this, and I have a vector Q which looks like this. So now if I have to add P plus Q, then what I will do is I will place the two vectors with their tips, or with the rear tips, at a concurrent point, and let us say this point is O. So for example, this was the vector P, this was the vector Q. So we place we choose a point O, we draw the vector P, and we draw the vector Q. So we draw these two vectors. Now they form in general two sides of a figure. We complete the parallelogram. So this parallelogram is to be completed. That means I will draw a line from P which is parallel to vector Q, and I draw a line from the tip of Q which is parallel to P. And here now the diagonal of the parallelogram this is equal to P plus Q. Let us say this is vector R. So we join the diagonal from point O, and this diagonal is equal to the sum of these two vectors. And this is how we define the parallelogram law for vector addition. So is this method clear? Basically the two vectors you draw together with the tips, and then you add up, you complete the parallelogram. The diagonal to the parallelogram gives you the resultant vector, or the sum of these two vectors. Now we can also alternatively we can talk of the triangular law. What do we do in the triangular law? We have a vector P, we have a vector Q, we have to add them. So first we draw the vector P. So stage 1, draw the vector P. Stage 2, at the end of P. Now I am talking of the front end of P where the arrow is. We draw the vector Q. So at this end I draw the vector Q. Now this will form in general two sides of the triangle, unless if P and Q are parallel to each other or anti-parallel to each other. Now the third side of the triangle, this gives P plus Q, which is what we are calling as R. So I draw the third side of the triangle. I write it as vector R, and the third side of the triangle gives me the sum of P and Q. And realize this is nothing parallelogram law, because if I on the same figure now I had vector P, and if I draw a line parallel to the vector Q, and from here I draw a line parallel to P, this is nothing but the diagonal of the parallelogram being completed. If instead of drawing Q there I drew Q over here, then this third side of the triangle was nothing but the diagonal of the parallelogram. So both of these lead to the same result, and this is how we add up vectors. So the definition of a vector becomes is a quantity such that two of them, if they are added, they will follow the parallelogram law of addition. So that is what defines a vector. Now let us look at some simple addition, simple rules for vectors. Well, firstly, we have what is called the commutative law. That is, if I add up two vectors p plus q, this would be equal to q plus p. That means it doesn't matter in which vector do I take first. I have vector p like this, I have vector q. If I start from p plus q, this is p, this is q, this is p plus q. Or I could start with q first. I start with q, then I move to p, this quantity which I get, this is equal to q plus p, and you'll realize q plus p and p plus q, these two quantities are equal. The two vectors will be parallel and they will have the same magnitude if p and q are the same. So this is what we call as the commutative law, and this we realize works for scalars also. A plus b is equal to b plus a, where a and b are scalars, and this law is the same for vectors as well as scalars. The second rule which we have for vectors is scalar multiplication, which comes from addition. For example, if I have p plus p, so this will be equal to vector p. To that I add another vector p, 2p. This itself forms a triangle. So this is p, this is p, and this total line which I have of this length, this is equal to r, which is equal to p plus p, and this is what we write as 2p. So we can think of this 2 as scalar which is multiplying p. And what we find is that if we have a quantity like, if we have a times vector p, where a is a scalar, then what we have is that a times vector p is a vector in the direction of p whose magnitude is a times the magnitude of the original vector p. And here now I will introduce for magnitude of a vector, which tells us what is the length of the vector, we use a symbol two bars. So if I put vector p within two bars, this will tell me the magnitude or the amount of length, magnitude of the vector p. That is what I term as the magnitude, and sometimes may also be written as without a vector. But normally we will put the two bars to make it very clear that we are talking of the magnitude. Now, after we have talked of this scalar multiplication, if I look at a quantity which I say is minus 1 multiplied by p. So here, if this is my vector p, minus 1 multiplied by p will be a vector of magnitude p, magnitude same as p, but whose direction is opposite. So this is how I define minus 1 times p, and so once I have defined minus 1 times p, I can define minus a times p. And this will be basically, you first let's say draw a vector a times p and multiply it by minus 1. So that will give you a vector minus a times p. Now this multiplication with a minus helps us define subtraction of vectors. And subtraction of vectors is nothing. But if I want to put two vectors and I want to say P minus Q, this will be nothing but P plus minus Q. So once again, if I try to look at it from a numerical perspective, let us look at what is, if there's a vector P like this, there's a vector Q like this. So let us look at it. What is P plus Q? So P will be P, we draw Q, and this is R is equal to P plus Q. Now I want to find R1 vector which is equal to P minus Q. So what will I do? I will first draw P. Now I will draw minus Q. So this is minus Q and I will add minus Q to P. So I do it like this, and this is the vector P